Welcome to EE221 Numerical Computing for Engineers. In this first introductory lecture, we'll give a broad overview of the course motivation and goals. We'll spell out the topics that we'll cover during the semester. We'll describe the overall course structure and the grading scheme. And we'll start looking at the Scilab programming environment, the environment that we will focus on in this course. Let's start with motivation. In our coursework, we learn the fundamental underlying theories which govern the behavior of the physical world. For example, Newton's law of motion. Force equals mass times acceleration, where force and acceleration are vectors, mass is a scalar, and acceleration is the second derivative with respect to the time of vector position r. Suppose now we want to apply that theory to understand the behavior of a pendulum. A mass m is suspended by a wire of length L from a fixed point. The angle between the wire and the vertical is theta, and the force of gravity pulling downward on the mass is F equals mg. If we assume that the wire is perfectly rigid and massless, then we can express Newton's law of motion in terms of the angle theta as follows. The second derivative of theta with respect to time plus the gravitational acceleration g divided by the length L times the sine of theta is equal to 0. This equation cannot be solved in terms of elementary functions. It can be solved in terms of somewhat exotic functions called elliptic functions. But if we want to get a solution that we can wrap our heads around, we're going to have to assume that theta is small. So there's an approximation. The angle of the pendulum can't be very large. With that approximation, sine of theta is replaced by theta, and now we can find a simple solution in terms of trig functions. Theta of t is equal to theta max times cosine omega t, where omega is the square root of g over L. Now, from a physical standpoint, this is a fairly simple problem, and yet we've already had to make an assumption about the angle theta in order to get an analytic solution. Now, what if somebody comes along and attaches a second pendulum to our first pendulum? Now we have the so-called double pendulum. Even if we assume that the rods or the wires are perfectly rigid and massless, we now have a pretty complicated problem to deal with. We can say some things about it if the angles are small, but what if the angles aren't small? What if we want to have large angles? Well, then we're basically sunk. In general, we cannot analytically solve the double pendulum problem. In fact, it often displays so-called chaotic motion, which is extremely complicated. We'll later, actually, in a few minutes, look at a numerical solution of the double pendulum problem, an even more complicated case where we allow the wires to actually stretch and be springs, which gives it 2 more extra degrees of freedom, which makes a particularly complicated problem. And yet, numerically, it's a piece of cake, as we'll see. So now, let's take a look at Scilab. To download Scilab, go to the scilab.org website, hit the download link, and it'll take a little while. It's about a 128 megabyte executable file. When it's done downloading, go ahead and run that executable, and it's fine to just default on all the questions. Should work for you. You agree to the license, and then all the directories and everything else just default. Takes a while to install, but when you're done, you'll have an icon on your desktop. I like to drag that over to my start bar at the bottom, and then you can open up and run Scilab. So here's just the console. It might look different when you first open it up. It has some other windows. You can go ahead and just close those windows, and then you can just type things into the console. X equals 2, x times x is 4, square root of x, and so on. And just for reference, we'll be talking also about MATLAB, which is very similar. Scilab is almost a clone of MATLAB. So here's the MATLAB console. You can see the same kind of stuff we do. So there are very few differences between the two. Scilab is open source and free, though. before we start learning Scilab specifically, I'd like to just kind of look ahead at some of the kinds of things we'll be able to do by the end of this course. Here I'm going to open up a program which integrates the equations of motion of a double pendulum. So, this is in a program file, and it's not too long. We'll understand all this stuff as we go through the course. So this takes three masses, red, blue, and green, and they're connected by two springs. The green mass is fixed, and then the other two masses fall under the influence of gravity and the springs. And you get very complicated, chaotic type motion. So there's really not much you can do with pencil and paper analytically to talk about this problem, but you can very simply solve it on the computer and generate an animation of its motion. You see over on the left, we're outputting various frames of what can then be tacked together into a nice little video file, which then can be put on YouTube or used as a presentation or what have you. Now let's look at a program that calculates the motion of some balls bouncing around on a table. You can think of it as a billiard table and billiard balls. So here we have an array that describes the position and velocities, initial positions and velocities of various balls on a billiard table. We go through, and in this case we integrate all the equations of motion up front and then generate an animation. So here finally is the result. We start off with one ball moving, and then eventually bounces into the other balls, and then you have them bouncing off the walls and off of each other. And again, this is a very complicated, high number of degrees of freedom mechanical system that you wouldn't be able to do much with pencil and paper. Now, let's go through and let's change up physical parameter here. We have the spring constant of the balls, how spongy they are. Let's make it much smaller so that they will be more bouncy or spongier. And now you can see how they don't, when they impact, it's not quite so sudden. The recoil, much more elastic. Okay, and we get a very different result. Different physical properties of the balls. Even though they start off in the same positions with the same velocities, we get a very different result because of the way the physics is different. One of the most foundational courses for civil and mechanical engineers is statics, and a very common statics problem is the truss problem, where we have various joints located in space, connected by various members, and then we have various reactions due to the mounting and applied forces, and then we want to calculate what the forces are in the members, either in compression or in tension. So here's an example of using Scilab to solve that problem. We end up with a program that has an array that describes the position of the joints and the applied forces, and another array that describes the members. We set up the equations of the static equilibrium, and we can generate a nice little graph here that shows the applied force in magenta, and then the labeled members have their compression forces. If it's a negative force, then it's actually a tension force. We can change the applied force to something else, rerun the program, and we'll get a different result. Okay, so we could have arbitrary numbers of joints and members, and we can do arbitrarily complicated problems, only limited by the amount of computing power we have at our disposal. We could treat the truss problem as a dynamics problem, kind of a hybrid of the last two examples we looked at. So we now allow the joints to have masses, and the members now are springs, and the joints respond. If we apply an external force, then there's a vibrational response of the whole system. We fix one point and allow the second base point to slide. An applied force at the top left corner. We can go and change the properties of the springs. Let's give it a little bit of damping so that the vibrations dampen down. And then we come into static equilibrium. We can make the springs stiffer, in which case there's not as much deformation. Or we can make the springs much spongier, in which case the whole structure fails. Okay, so wide variety of problems that we can attack. So now the purpose of this course is for you to, first of all, learn fundamental numerical methods so you can understand how to formulate numerical solutions to difficult engineering problems. And secondly, to develop the specific programming skills, in our case using the Scilab MATLAB environment, so that you're able to effectively implement your numerical solutions. Now, eventually you may work on a project where you want to implement a programming solution with another type of environment, maybe a higher performance compiled type of programming language or what have you. But all of the basic programming skills you're going to learn in this course will very directly translate over into those environments. And in many of the problems you will deal with as engineers, you will be working in something, either MATLAB or something very similar to it, most likely. Okay, so very applicable to many of the problems you will work on both as a student and as a practicing engineer. So here are the topics that we will cover in this course. I've broken it down into 15 topics corresponding roughly to the 15 weeks of a semester, and we will have at least nominally 2 roughly 50-minute lectures per topic and roughly 1 homework assignment per topic. So first of all, what we're doing now, the introduction to Scilab and numerical computing. Then we'll talk about arrays and vectorized functions. The ability of this environment to handle arrays is one of its strong points. In fact, MATLAB is short for Matrix Laboratory. It was developed, I think, back in the early 1970s as a tool to help students more effectively work with and learn linear algebra and the manipulation of matrices and vectors. We'll see that's a very powerful aspect of it. Then we'll talk about programming structures and input-output, how to write a basic program, how to get information into the computer, either from the keyboard or from files, and out of the computer, either to the screen or to files, possibly even spreadsheets and things like that. And finally, for the introduction to programming section, we'll have introduction to graphics. How do we now output our data in a form that we can look at? We just saw some animations. That'll be one aspect of that. How can we, have a physical problem that might be fairly complicated, and then we visualize it as an animation or as a figure? That's very important to be able to do. So how do we produce those, and how do we make a nice presentation quality graphic? Then the meat of the course is in numerical methods. So the first part is just how to write a program, the basic stuff that goes into that. Now, what do we put in the program? Well, we start off with root finding. How do we find the solution to an equation, say f of x is equal to 0? Linear algebra, the manipulation of matrices and vectors. And as I've already alluded to, this is a very strong point of the Scilab, MATLAB type environment. Matrix decomposition, sort of a special topic in linear algebra. Very important in all kinds of areas of applied engineering, but for example, in analyzing the vibrational modes of a complex structure, a bridge, or a piece of a machine or something, you get very often into this problem of finding the eigenvalues and eigenvectors of a matrix. So we'll see how to do that. Least squares curve fitting. A very common problem is that you have some sampled data and you want to fit a smooth curve through those data to represent some underlying function. Related to that is interpolation. You have some sampled values from, say, a function or some process, and you want to find out the values for different conditions than what you sampled, and so we do interpolation. Numerical integration and differentiation, just numerical calculus. How do we do the numerical integral of a function if, say, we can't analytically perform the integral? How do we numerically approximate derivatives? Optimization. So this is the idea of being able to maximize or minimize a function. So very often engineering problems can be set up as, say, a performance indicator that somehow takes into account the the physical performance of the system and its cost and all the various things that go into it, and you want to, say, maximize that performance indicator. How do we do this numerically? Random numbers and probability. How do we generate and manipulate random numbers and probability distributions and measure and plot and graph probability distributions? We'll have an introduction to differential equations. Differential equations is not a prerequisite or co-requisite to this course, unlike linear algebra. But we will just have, it's so important in engineering, and it will be so important in your future courses, that we want to have a brief introduction to that, just to show you how to deal with differential equations numerically on the computer. Then when you take your differential equations course, when you start applying differential equations in your engineering courses, you'll be able to come back and use this environment to get solutions to those equations. In fact, most of those examples we looked at with the animations were solving differential equations. A couple additional topics as time permits. Program development and libraries, kind of the overall idea of debugging programs, of building programs, maintaining programs, documenting them, putting useful functions together in a library that can be reused, some kind of high-level issues. And finally, the user interface, specifically a graphical type user interface. Can we develop sort of an interactive environment in which we can use the mouse and keyboard and other things in order to make decisions in the program or input data graphically and things of that nature. So now let's go ahead and get started with Scilab. We're just going to use the console here. Eventually we'll learn to open up the program editor and to actually generate program files on the disk. So what can you do with Scilab? Well, one of the first things we'll do is just to use it like a calculator. Let's say we want to calculate 10 plus 6 over 3 minus 4 times 2. Hit enter, and there's our answer. It's 4. We could have done that in steps. Now notice we get at the end of that calculation, we get a variable ANS, answer, is equal to 4. That's an actual variable which I can type in, and it represents that answer. It's just like our sort of our register that's in the calculator. We can just take the result of the previous operation and do something else to it. So we could have done it this way, step by step. 10 equals 10. Okay, that answer plus 6 over 3 equals 12. That answer minus 4 times 2 is equal to 4. And we get the same answer 4 that we got by putting everything in all in one line. Okay, so that's useful, using that answer as the final result from the previous calculation. Okay, this also brings up an interesting thing. Notice, let's go back up here. Now, another thing you can do is if you use the arrow keys, the up arrow allows you to scroll through your previous operations. So we can go back here, right? And then I can also use the left and right arrows. If I wanted to change the 6 to a 4, I could use now backspace 4 and then get a different answer, right? So let's now take a look at this operation we did here that gave us the answer 4. 10 plus 6 over 3 minus 4 times 2. Now, what if we wanted to actually calculate 10 plus 6 is 16 divided by 3, and then minus 4, and then that whole thing times 2. Let's take a look at that. We could go like this. 10 plus 6 is 16. That answer divided by 3, 5 and a third. That answer minus 4, 1 and a third. That answer times 2 is 2 and 2/3. Okay. Now, why don't we get the same result if we just type that in the same order all in one line? 10 plus 6 over 3 minus 4 times 2. It's because of the idea of operator precedence. And many calculators implement this same concept, and it's nearly universal in programming languages. It's assumed that multiplication and division take precedence over addition and subtraction. So Scilab will go from left to right along your expression, performing operations, but it'll first do multiplication and division, and then it'll go through and do addition and subtraction. So here it goes through. It first takes 6 divided by 3 is 2, and then here it does 4 times 2 is 8. So it does 10 plus 2 is 12 minus 8 is 4. Now, if we explicitly wanted to calculate 10 plus 6, that addition is 16 divided by 3, we would have to put in parentheses to override the operator precedence. So we could do this. 10 plus 6. Now in parentheses, that's going to be done first. Divided by 3. And now we want that whole thing, subtract 4 from it, and then multiply the entire result by 2. And now we get the result that we got in stepping through one at a time where we didn't have the operator precedence. Now another thing you can do on your calculator is to use functions. Well, you have like the trig functions, for example. So we can do the same thing in Scilab. The sine of 0.5. What is it? It's 0.47942. Okay, well, when we say sine 0.5, what does 0.5 represent? All right, well, just as calculators typically default to radians, programming languages implement the trig functions in their mathematical form, in which case the argument is assumed to be radians. All right, so sine of 0.5 means sine of 0.5 radians. What if I really wanted to do, say, the sine of 1 degree? Well, I could first convert the degree to radians. How do you do that? Well, there are pi radians in 180 degrees. So this would be 1 degree times pi, which is 3.14159, over 180. That would be one way. Or Scilab gives you the ability to do kind of like you do on your calculator when you choose degree mode. If we say sine d, that means that the argument is in degrees. Sine d of 1 gives us that same result. Likewise, cosine of 1, cosine d of 1, tangent of 1, tangent d of 1, and so on. Okay? So you've got the trig functions, and then if you append a d to the name, you now assume that the argument is in degrees. We also have the inverse trig functions. Now that would normally on calculators be written as like sine to the -1 power. In the ASCII text that we use to write our programs, we implement this as the so-called arc sine. So we say a sine, the arc sine. So what's the arc sine, say, of 0.5? What angle has a sine of 0.5? 0.5, 2, 3, 5, etc. Again, it's assumed that you're working in radians. So that angle is going to be in radians. That's an angle in radians. So we could either take that and multiply by 180 over pi to get the degrees, which is basically 30 degrees, or we could say a sine d, for meaning we want the answer in degrees, of 0.5. And likewise, we've got a cosine. Oops. And a tangent, the inverse tangent. Let's do the inverse tangent of 1. Okay, what's the inverse tangent of 1? It's 45 degrees, or pi over 4. So if we want it, we did a tan, there's no d there, so that's in radians, so we want a tan d of 1, and there we go, it's 45. Now there's a subtle issue with the inverse tangent. Let's take a look at this. Let's choose an angle of, and let's say this is in degrees, let's take 135 degrees. Okay, what's the cosine of 135 degrees? And what's the sine of 135 degrees? Well, the same number, but with the opposite arithmetic sign. So the tangent, which is going to be the sine over the cosine, is going to be -1. And indeed, tangent d 135 is -1. So what's the inverse tangent? A tangent d -1. Is it 135 degrees? No, it's -45. Why is that? Because the tangent of -45 is the same as the tangent of 135 degrees. Why is that? Because the sine of -45 degrees over the cosine of -45 degrees is the same as the tangent that we get for the 135 degrees. However, notice the sine of -45 degrees is not the same as the sine of 135 degrees. In fact, they have a different arithmetic sign, don't they? And likewise, for the cosine. And so you lose the information about that difference of the sign between the cosine and the sine functions when you take the ratio to get the tangent. So if you want to explicitly be able to get inverse tangents that go around all the way from minus 180 to plus 180, you have to use a special form of the inverse tangent or the arc tangent. You'd say this. So let's take a look at this. A tangent in degrees now, and let's put in the tangent of 135 over cosine of 135. I'm sorry, the tangent of 135 degrees, which is the sine of 135 over the cosine of 135. And as we saw before, we get minus 45. Again, we lost the information about the fact that the tangent of 135 is the same as the tangent of minus 45. So the inverse tangent doesn't know which one. So it could be, so it just gives you the one that's between plus and minus 90. In order to get rid of that ambiguity, you do this. You give the y value, or the numerator value, and the denominator value here, and now it can figure out that it's 135 because it explicitly knows the sine value and the cosine value separately. Okay, so that's called a 4-quadrant inverse tangent. So that's just something to keep in mind later. If you're using inverse tangent, you have to be able to figure out the angle all the way from minus 180 to plus 180 degrees. You need to use that 4-tangent form. All right, so those are basic trig functions. And again, we can always go in and do help here. And here's Scilab. Here's keywords. We can come in and look at elementary functions. And we go down here, trigonometry. And there's all the trig functions. You can see a whole bunch of stuff, and you can go through and look at any one of those. All right, here's the secant, and the hyperbolic secant, and the hyperbolic cotangent, and everything else. So the help is always a great way to see what all the options are. Let's now look at some other basic functions. We have the power operation. 2 to the third power, we use 2 to the hat 3. All right, so that's 2 times 2 times 2. You can use fractional powers and negative powers. 2 to the minus 0.37, okay, which should be 1 over, 3 to the minus 0.37 I did, which would be the same as 1 over 3 to the 0.37. Yes, it is, indeed. Okay. Now, for square roots, you could say, what's the square root of 2? Well, you could say 2 to the 1/2 power, but square roots come up so often that there's a special function for that operates a lot faster than the full power method, and that would just be the square root, SQRT. Okay, so that's preferred for square roots because it is faster. The exponential, we do it this way, EXP, the exponential of, say, 3.2. So that's e to the 3.2. Natural logarithm. Now this is a little bit confusing. Programming languages follow this standard, which is the traditional math notation that's not exactly followed by engineers. And that is that the natural logarithm is log. So what is the log of 10? Well, very often in engineering we've come to use log to mean the logarithm base 10. We would assume that the log base 10 of 10 would be 1, because 10 to the 1 is 10, but it's not. It's 2.302. That's actually the natural logarithm. Log, ln, which we usually use on our calculators, isn't defined. So it says undefined. So we use log for the natural log. And that's typically true with all programming languages. So what about the log base 10? Well, you can get the logarithm to any base by dividing by the natural log of that base. So that'd be log base 10. Log of 10 over log of 10 would be 1, which is the log base 10. Or we have this shorthand, because log base 10 is so common, log 10. Okay? So how about log 10 of 100? Well, 100 is 10 squared, so the log base 10 would be 2. But notice that log 100 will be the natural log of 100. It's 4.605. That means that the exponential of that is 100. Okay, so that's just a little wrinkle there that you see the same thing in Fortran and C and other languages that you have to keep in mind. Another thing that's sometimes useful, right? We got our answer here. If I type in clear and now put answer, it says undefined variable. That clear has cleared everything out of the memory. It forgets everything that Scilab's done and starts fresh. If I also want to clear this console screen, by the way, CLC for clear console will do that for me. So now let's look at going beyond arithmetic and just entering in numerical values and getting numerical values out. What you can do on your calculator that's often useful is you can use registers to basically store values and then operate on those registers. So in a programming language, we have a similar idea. We have variables that we can define. We could say x is equal to 2. And now later if I say x, right, so that's a variable that's been defined. And variables don't have to just have any particular name. I could say spring constant is equal to 3.7. So anything that's a valid string basically can serve as the name of a variable. So I got my variable x here. Now I can operate on that. I can say x squared plus 3 times x plus 7. All right. If I change x now, say to 4, I can use my arrow keys to bring that formula back up and recalculate it for the new value of x. I can likewise do cosine of x and so on. Okay, I could assign that result to a new variable. Y is equal to the cosine of x. Now I've got x and I've got y. So that's basic variables. And in fact, most of the numerical computing we will do will be based around variables, applying formulas to variables and then making decisions based on the outcome of certain tests, whether to terminate our numerical algorithm and so on. So variables will be very important. We'll keep coming back to those time and time again. So these are now numerical variables, and specifically floating point variables. In MATLAB, Scilab, decimal values, let's say I is equal to 3, is actually, you'll notice it shows as 3 point. It's actually stored as a floating point number. By default, all variables are floating point numbers. We can make use of it as an integer. It's just 3.0, but we could still go and say square root of I, and I could be equal to that, and now it's not an integer anymore. So there's no so-called typing of variables as there are in compiled languages like C or Fortran. The variable is whatever you assign to it. If it's a decimal, an integer, it's an integer. If it's floating point, it's floating point. And likewise, a variable can also be a string. We can say A is equal to. Now, for strings, we need to quote, and everything between the quotes will be the string variable. This is a string. Okay, in quotes. There you go. A, this is a string. Okay, let's do another one. String B is equal to space, and here is another string. I mean, I got A and B. And what's A plus B? Well, for strings, that just stacks them together, and we get this as a string, and here is another string. Okay, so that's pretty useful because we can use that to label things and to build up more complicated output from various maybe error messages or things that we want to string together. Something that sometimes is useful is that we can convert a number to a string. So let's look at this. Let's say x is equal to 1.234. We can do xs, say as x string, or xtr, maybe for x string, is equal to string of x. This is a function. Well, now xtr is 1, 2, 3, 4, but now that's a string. And we could say, let's do a is equal to, the answer is plus string of x. Now we get a single string that says the answer is 1.234. And a is now that string. Okay, so we can use also some of these operations to build up nicely formatted output. And something like that could obviously be very useful for displaying an answer and letting the user know what the result was. Okay, so that's variables. Just a quick introduction to variables. There are special types of variables we call constants. Now, consider, for example, the number pi. Okay, so I could define a variable. Pi is equal to 3.14159.265 or whatever it is. I can't remember all the digits. Right? We could do that. It would just be a variable, say called pi. That might be a little risky though, because I may inadvertently go and redefine it, and now it's no longer really equal to pi, right? It's not a very good constant if I can redefine the value. So Scilab gives us a so-called protected variable or constant syntax here. % pi is a predefined variable which is equal to pi. Now let's try to change it. % pi is equal to 3. Redefining permanent variable won't let you do that. Okay, one very important constant is the imaginary unit. %i. Predefined variable, right? I can't reassign that to some value. %i, which is the imaginary unit I using standard math notation, squared is -1. I is the square root of -1. Now, often in engineering we use j for the imaginary unit. We could do this here by defining a variable j to be equal to %i, and now j squared is -1. And then we could form complex numbers like z is equal to 2 plus 3 times j. And notice that Scilab will echo that back to you using I as the imaginary unit. Now, unfortunately, if you do that, j is just a regular old variable. And you could inadvertently redefine it yet again. And now you're not going to get the right result. Okay? So that's one little trickiness about using a variable for what you really want to be a constant, is that you always have the danger that you would redefine it. So I prefer to just use the built-in protected variables. But again, if you want to, and you're careful about not redefining it, and you'd rather use j, you can make this definition and then just make sure you don't redefine j. Okay. When we talk about multiplication with, let's say we have two complex numbers, u is equal to 1 plus 2 times I, and v is equal to 2 plus 3 times I, u times v, we'll get the complex result, real and imaginary part, or u over v, right? Or we could even do u to the v. That makes sense if you remember back to your calculus, complex numbers to a complex power, and so on. So we can operate likewise to do trig functions. What's the sign of u? What's the sign of a complex? Well, you got to go back and remember Euler's formula and all that. So we can operate with complex numbers, complex variables, just like real numbers. All right, now one of the things, let's clear everything here and start over. We notice if we're doing calculations, we say like 10 plus 2, okay, that answer plus 4, and that answer times 3, and so on. Notice every time we enter, Scilab spits out the answer of that particular calculation. And maybe I don't want all these answers equal to stuff coming out. Let's see what we can do. 10 plus 2, semicolon. Notice what happens. Scilab does not echo anything back at me. And then I can say answer plus 4, semicolon. No echo. Answer times 3. Now, semicolon, I get no echo. Now I can just say answer, and there's my result, 48. So I can suppress the echoing out of the intermediate result by putting a semicolon. And in fact, when we write programs, every one of our statements essentially will have a semicolon at the end. But when you're doing things interactively, that's just a way to suppress all of these intermediate results if you don't want to see them. All right, let's see. Another thing that sometimes occurs, if let's say we do this. What is e to the 50? Okay, well, let me try this. E to the 10. There we go. That's a pretty big number, right? 22,000 and something. Up here, we see the number was so big, we got what's called the scientific notation, or exponential notation. But let's look at something kind of in between. 22,000 and 26. Okay, that's a pretty big number. Or what if we did exponential minus 10? Okay, that's a very small number. What if I want that in scientific notation like we got up here? If it's too big to display in normal decimal point notation, you'll get the scientific notation. But if by default you want the scientific notation, you can do this. You can give Scilab a format command. You can say format string E. Now let's do e to the minus 10, and notice what happens. We get it in scientific notation. If we want to go back to the other format, we go format string character V. And now we're back to the other format. We can even add another argument to this. Let's say we want to have more digits in our output here. We can do this, format E10. Now we do e to the minus 10. Okay, we should have 10 characters across there. Make it 20. Now notice I get 20 characters, and so on. So I can control the type of format, whether it's with the rather kind of decimal point, fixed point format, or the scientific exponential format, and the total number of characters that comes out. Again, you want more information about that? For anything we talk about, just say help format, go through, and you'll get a description of this. Now suppose you have a Scilab session and you're going along and doing some calculations and so on and so forth. String equals an example. And you want to save this session, the output of the session. I mean, you want to actually save this text. How do you go about doing that? Most straightforward way is you just go up to edit, select all, copy, and open up any basic text editor and paste. All right, so here's just Notepad, and there you go. There's a little record of your session, and save it, and away you go. So that's probably the most straightforward way. Another little more formal way is to use the diary command. So we could do this. So let's see what directory we're in. pwd, print working directory. So I want to go to my desktop, and now I want to do this. Diary, and it doesn't have to be on your desktop, but I just want the file there. Example.txt. Okay, so diary file name in quotes is going to put everything that I type into this Scilab session into that file until I close the session. Okay, so now I can do things like, x is pi, y is equal to x squared, and so on. And so on. When I'm done, I just say diary 0, which means close all open files. And now anything else I type in there, like z is equal to 3.7, should not appear. I go to my desktop. Here we go. And here's a file called example. Notice everything after I had the diary command is in there. And here I closed it. And then after that, when I had the other commands I put in, z is equal to 3.7, that does not appear because I've closed the file. So that's another way to save your interactive session. The title of this course is Numerical Computing for Engineers. Now the operative keyword there is numerical. We're talking about numerical methods. We're doing calculations, arithmetic calculations with numbers. That's as opposed to ideal algebraic calculations, analytic calculations with symbols. And when we deal with numerical values, there are some issues that come up, and most importantly, the finite precision with which we can store numbers. So let's look at this. Suppose I say x is equal to 10 to the minus 20th power. Okay, so here's the notation, scientific notation. That's 1.000, etc. d, or which represents double precision, is the same as the exponent, d minus 20. That means times 10 to the minus 20. Okay, so that's the representation. So that's fine, exact representation of 10 to the minus 20th. What if I now say 1 plus x minus 1? What should that be? It should be equal to x, right? 1 minus 1 is 0 plus x. So I should get 10 to the minus 20th, but I get 0. Why is that? There's a problem when we say 1 plus x. Let's just write it out. We know what it would look like. It'd be 1 plus 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And there's the problem. Too many digits, right? Let's go back here and take that, minus 1, 0. Why? There are just too many digits required to exactly store this value. And Scilab stops at some point. Now, it actually doesn't store things in a decimal format. It stores things in a binary format, and it uses 64 bits, a so-called double precision floating point format to store numbers. So it isn't a one-to-one correspondence with decimal digits and binary bits, but there's a rough correspondence, and you can figure that out just by doing this problem of, let's write it this way, 1e minus 6, say. Right there. Oops, and let's go into our exponential format. So there's 1 plus 10 to the minus 6 minus 1 is 10 to the minus 6. No problem. We know that 10 to the minus 20 doesn't work. How about 10 to the minus 10? Yeah? How about 10 to the minus 15? Almost. This should have been 1e minus 15. It's 1.11. Why is that? Well, we're getting down in the binary domain to where our digits are like falling off, kind of analogous to this expression, but in binary numbers. And so what that does is it, instead of losing a full decimal digit, it kind of loses part of a decimal digit. Okay, 10 to the minus 14th, well, still not exact. 10 to the minus 13th, 10 to the minus 12th, pretty good. Okay, so we can see there's some limitation. 10 to the minus 17th, now we get 0. 16th, 15th. Okay, so we're kind of at the limit here, about 16 digits, roughly. 15, 16 or so digits. We can't store 20. We can certainly store 6, but at about 15, that's about the limit of our precision with which we can store numbers. So that's something we have to always keep in mind. Now you might say, and this is the same thing is true with your calculator, by the way, might say, well, that's plenty of precision, 16 digits, no big deal. And why would I do some crazy thing like this, 1 plus 10 to the minus 20th minus 1? Well, these kinds of issues do come up when we do our various numerical methods. And let's take just one look at that. Look at the idea of the derivative of a function. So if we want to look at the derivative, let's say, for example, we're going to look at the derivative of the exponential function. Okay, so what would be the derivative of, so if we have e to the 0, that's 1, right? But what's the derivative of e to the x at x is equal to 0? What's the definition? Well, remember your calculus books, we define, in principle, a small quantity, small number delta. Let's make that be 10 to the minus 6th. And we say that the derivative would be e to the x, which is 0 in this case, plus delta, minus e to the x, which is e to the 0, over delta. And in the limit that delta goes to 0, that is the actual definition, the analytic definition of the derivative. So numerically, we can't let delta go to 0. We can't do a true limit, but what we do is let delta be very small. Now, so how small is very small? Well, what about 10 to the minus 6th? We know what the derivative, e to the x, it's its own derivative. So the derivative of e to the x equals 0 is just equal to e to the 0 is equal to 1. And there we go. That's a good representation. E to the delta minus e to the 0 over delta. Now, since this is exactly true in the limit at delta goes to 0, we would expect that as delta gets smaller, right, this approximation should get better. Okay, there, very good. How about 10 to the minus, how about 10 to the minus 20? Wow, now we get a derivative of 0. What happened? Well, it's our old round-off error problem, right? E to the 10 to the minus 20 is so close to 1 that the difference is way out here in so many digits of accuracy, of precision, that we can't store it in the computer. So when we do this difference, we've got a tiny, tiny difference of numbers that are close to 1, and we don't have enough precision to actually accurately represent that difference. And so this just becomes 0, okay, which is completely wrong. The actual derivative is 1. So there's a case where we would say, well, in this formula, e to the delta minus e to the 0 over delta becomes closer and closer to the true derivative of value of 1 as delta gets smaller and smaller, but numerically it doesn't. On the other hand, right, if delta is too big, let's say delta is just 10 to the minus 1, so then our estimate of the derivative is off by about 5%. So we say, well, make it smaller. Estimate will get better. Yeah. And so on and so forth. And we might say, well, then make it really, really small, right? And again, that's the problem, is that we're forgetting about this limitation, numerical limitation, the fact that we have a finite amount of precision and we have to think about round-off error. So that's going to be a really important thing. We actually will come across this in many of our algorithms, and we'll have to give that some thought. Worrying about round-off error. It isn't always the case that making values smaller will give us more precise results.